In this discussion video, we will do a practice problem involving finding what's wrong with a certain epsilon delta argument. So this is problem number 9 from worksheet 3, where we have this piecewise function, and I want to first give you 7 minutes to try this. So pause it in 4, 3, 2, 1. Pause that video, pause it for 7 minutes to really try this question. Alrighty, so hopefully you've done that. Hopefully you paused it and tried it for about 7 minutes. Let's talk about it together now. So in part A, it wants us to first find these two one-sided limits, and then based on your answers, we try to conclude something about the overall limit. Alright, so first let's find the limit as x approaches 1 from the right. And as you approach 1 from the right, that means x is bigger than 1. So this equals the limit as x approaches 1 from the right. And if we're bigger than 1, that's talking about this top piece of the piecewise function. F of x is going to be x squared. And now let's go ahead and plug in the number 1 straight up. So we'll get 1 squared, which is just 1. Let's do the limit from the left. As we approach 1 from the left, that means, this now means that x is going to be less than 1. So we get the limit as x approaches 1 from the left. And if we're less than 1, that is now the bottom piece. So we're going to be plugging 1 into this bottom piece. 2x minus 1 over 3. Now let's try plugging in 1. And we get 2 times 1 minus 1 over 3, which is just 1/3. So those are our one-sided limits. And now it asks us to say something about the overall limit. Well, since the one-sided limits are different, since the one-sided limits, I'll abbreviate limbs are different. The limit as x approaches 1 of f of x, that limit does not exist, or DNE. All right, let's look at part B now. Part B is asking us to find a value of delta such that when 0 is less than the absolute value of x minus 1 is less than delta, then the absolute value of f of x minus 1/3 is less than 1. So this is one of those questions where it gives me a specific value of epsilon. The epsilon is here. It's 1. And it wants us to find a value of delta that sort of works. That'll guarantee that we are within this epsilon equals 1 window. So this number that goes with x over here is a. So a is going to be 1. And then this number over here, this 1/3, that's L. Okay, so one thing that's going to help us in problems like this is to draw a picture. To draw a picture of our function, which is this piecewise function. So let's first draw a picture of x squared and the bottom piece. And then we'll put it together as this piecewise function. Okay, so let's talk about a picture. So we'll do the graph of y equals x squared. Then we'll do the graph of y equals 2x minus 1 over 3. And finally, we'll piece it together. We'll take a piece of each of those graphs and put it together as this piecewise graph. So let's draw some axes, and some axes. Y equals x squared is a upward-facing parabola with a vertex at the origin. Y equals 2x minus 1 over 3, we actually want to simplify this. We can split this up into two fractions, 2x over 3 minus 1/3. And now this is actually an equation of a line, because this term is 2/3 times x. The y-intercept of this line is negative 1/3. Okay, so let's label that negative 1/3. And then it slopes upward. The slope of it is 2/3. So kind of flattish, something like this. And with both of these graphs, I know that we're going to have to sort of split it when we reach x equals 1. So let's find the point on each graph where x does equal 1. On this graph, when x equals 1, if you plug that in, you'll get 1 for the y value. In fact, we could see that. We actually did that up here when we did this one-sided limit. We literally plugged 1 into it. And with the other piece, we also plugged 1 into that, and we got 1/3. So that's how I know that when we plug 1 into this one, this y value is going to be 1/3. So our piecewise function says, well, it's going to be this line equation when x is less than or equal to 1. And then it's going to be the parabola equation after that, after x is 1. So that means it's going to be this part of the line equation before 1, and it also includes 1. Also includes 1 because, because of that equal sign, x is less than or equal to 1. And then it's going to be the parabola after 1, which means I'll have an open circle, and then this part. So putting that together, we will have a line that looks like this. And once I reach x is 1, this y value is a third. And then at x equals 1, then it jumps to being that parabola shape. And the graph looks something like this at a y value of 1. All right, so I've gone ahead and just redrawn the graph, but just a little bit larger, and copied the delta and this epsilon statement that we're working with. So remember that we're working with a specific value of epsilon equal to 1. And based off of this setup, it's saying that L is 1/3. So it's kind of saying, oh, the limit is 1/3, which is weird based off of what we found out. We found out the limit should be does not exist, because from the left and from the right it's different. But let's go with it and see if we can still find a delta that works in spite of that. Okay, so epsilon is 1. We need to go a distance of 1 away from y equals 1/3. So I can go a distance up of 1. That'll take me past the 1, distance of 1 this way, epsilon equals 1. That'll take me up to 4/3. I can also, let's draw that better. That's the distance of 1. I can also go a distance down of 1. In fact, let me put these here. Distance down of 1. Give myself more room. That distance is 1 as well. And if we go down 1, this y value is going to be negative 2/3. Now let's draw our epsilon window. So I'll draw these horizontal lines. This time I have to draw the horizontal lines to the left to actually intersect the graph. So it intersects it here. Let's do the same thing for this at the y value of 4/3. So I want to know the edges of this epsilon window. I want to know what's going on at this point, what that x value is, and I want to know what's going on at this point and what that x value is. So to find that second one, I need to know when that line has a y value of negative 2/3. So the line equation was 2/3 x minus a third, and I want to know when that equals the y value negative 2/3. Similarly, to get the 4/3 one, I'm going to have to set something equal to the y value 4/3. And it's the parabola piece that needs that y value. So I'll be setting x squared equal to 4/3. Okay, let's solve this line equation first. If I add 1/3 to both sides, we get 2/3 x equals negative 1/3. And now I'm going to multiply both sides by 3/2. So we get x equals negative 1/3 times 3/2. The 3's cancel, and I get negative 1/2. All right, so this x value is at negative 1/2. Now let's solve x squared equals 4/3. Square rooting, we get x equals plus or minus root 4/3. And because our parabola is only defined when x is greater than 1, it can't be the negative x value. So this can't be negative since x is greater than 1 on this piece of the graph. So that is going to mean that x is just the positive root. So it's positive, and then I can take the root of 4, that's 2. I get 2 over root 3. All right, let's label that as well. So this x coordinate is 2 over root 3. So now I need to find a number for delta that'll guarantee that when I go a distance of delta away from 1, I'll still be in this epsilon window. And it definitely looks like this point on the right is a lot closer to 1, but let's be careful just in case I haven't drawn things to scale. Let's actually find the distance from 1 to each of the endpoints here. So from 1 all the way to negative 1/2, that distance is going to be 3/2, which is 1.5. And with 2 over root 3, I can estimate this a little bit. This is 2 over, and I know square root of 3 is in between square root of 1 and square root of 4. So it's 1 point some stuff. And if you divide 2 by 1 point some stuff, that's going to be 1 point some stuff. It's going to be 1 point something. So that definitely means the distance from 1 to 2 over root 3, that distance is less than 1. So that's definitely the shorter distance. So I believe this problem said we could pick any delta that we want. It doesn't necessarily have to be the largest one. But let's just go ahead and pick the largest possible delta. So if I go from 1 all the way to this right endpoint here, that delta is going to be 2 over root 3 minus 1. I can also go that distance in the other direction. And if I look at this range of values, I put an open circle here, and then I shade it in up until this point. I can't be right at 1. Same thing here. Shade these in, open circle there because I can't be right at 1. And all of those red shaded areas are in the epsilon window like we need. Okay, so the value of delta that we picked was 2 over root 3 minus 1. Smaller values will work as long as you make them positive, but that's the biggest value of delta that'll work here. All right, let's look at part C. Part C is saying, wait, in this graph, if we let epsilon be equal to 1, we found a delta that works. That makes us be in the epsilon window. Part C then asks, well, does B show that the limit as x approaches 1 of our function equals a third? And the answer to that is no, it doesn't. We would hope that it doesn't because intuitively the limit should be d and e. But the reason is that B just shows that if epsilon equals 1, we can find a delta that works. But for this limit to truly be a third, like it's claiming it is, we would need to show that for all choices of epsilon greater than 0, no matter how small, that we can find a delta that works. But we haven't done this. But, kind of getting a run-on sentence. Let's just start a new sentence. But we haven't done this. But we have not done this. So, we can't say that this limit is a third. Limit as x approaches 1 of f of x equals a third. We cannot say that.